So hello again and welcome to this webinar series for Advanced Numerical Modeling Techniques for Tunnel Analysis. My name is Chinmoy and I'll be your host for this session. So in this ongoing webinar series, we have covered three sessions till now. So today is the fourth one and this session is quite related directly to practical field modeling. So those of you who attended the previous session for overview of NATM tunnel design methodology and are familiar with the GRC and SRC design and LDP methods, you will find it comprehensive to go from 2D to the 3D modeling by the help of this particular session. So this session is directly correlated to the previous one. Okay. So this particular session is where we will cover the same NATM methodology but in 3D. So we will have three different models this time. So we will cover all the kinds of supports present for your NATM analysis, and then we'll proceed on how to interpret the results. But in the same time, I'll also show you how to model various types of support elements in FEM analysis using GTSNX. And if you have any questions, I'll request all of you to reserve your questions till the very end. We'll have a short 10 to 15 minutes session for Q&A, where I'll try to cover most of your questions to the best of my abilities. So starting with the contents for today, I'll just have a brief glimpse on the methodology or the brainchild behind NATM modeling. Then I'll just show you what we plan to show you today in terms of modeling approach. Then finally, we'll go to the numerical model. And towards the end, I'll show you the exclusive offer that we have as promotion for the current series. So this presentation will be a bit short one because most of our time will be focused on modeling and result interpretation. So we'll start with theory behind the NATM method or Dillon blasting method. So basically, Dillon blast method is one of the oldest forms of tunneling because this method is actively employed in mining. So some of you who might be mining engineers, they might be very much aware of all the activities that have been shown in here. So the entire chain of process starts with a survey, like where we have to drill and what kind of material is present. Then post survey, the holes are marked. Then we go to the drilling phase. So normally for tunnels, you will either use a Simba or a Jumbo from Sandvik for drilling. And now these machines are coming with laser guided precision. So drill hole deviations are quite low currently. If you rewind the times 10 to 15 years back, the deviations used to be quite high in terms of drilling because of the pressure inside the rock and the stress that the drill rod have to take. So there used to be a lot of deflections. In open pit scenarios, drilling is not big of a concern because you still get some area to play around. But in underground, where your space is highly constricted, drilling has to be spot on. Otherwise, it creates a lot of issues while the mucking process. So after your drilling is complete, we will load the drill holes with explosives, let's say ANFO or a dynamite or side mixed emulsion or side mixed slurry. Post loading and your charging has been done, then the detonation will take place. Post detonation, it is right now the primary regulations state that the noxious fumes have to be cleared. So you have to give a bit of time, let's say 2 hours or 3 hours, depending on your current phase location or depending on your ventilation capacity for the noxious fumes to dissipate. Otherwise, it creates a working hazard for the for the staff working in that particular phase. Post clearance of the noxious fumes, then the machines come over and take over the entire mucking process. So either you will use LSD or LPDT to clear the area, and depending on your size of your tunnel, let's say if the tunnel height is quite big, you can also use excavators for that. Once the dislodged muck or the blasted muck has been cleared, you have to go for a scaling operation, because scaling is what is going to clear your clear the phase for you, and it will give you the final phase. So in this scaling operation, it is required to give the final peripheral shape of the perimeter, and at the same time, if there is any overhanging rock or loose rock along the walls or along the roof, they will be cleared up. Post scaling, you'll have the bolting and shotcreting and whatever kind of reinforcement is required based on your rock RMR value, and then the process repeats itself until the breakthrough is achieved. So after this part is clear, we'll just have a brief glimpse on what is the basic ideology behind NATM progression. So NATM design philosophy can be broadly divided into two categories. First being the design criteria related to NATM technical requirements, and the second is design criteria related to external constraints. So when we come to the first part, that is the criteria related to the NATM technical requirements, the area will be first investigated properly, and then the primary support will be planned out. Post that, the monitoring systems will be installed. Then the final support will be done. So ground investigation will lead you to what kind of geometry, size, and excavation pattern is good for that particular area, because you cannot have you cannot have too big of a tunnel in, let's say, weak ground or heavily squeezing conditions. That is why these ground investigation, they lay the foundation stone for any upcoming kind of work. And NATM, as we all know, is basically like you see, you monitor, and then you improvise on site. So it is mostly an improvisation based process. That is why in NATM methodology, monitoring is the paramount thing that you have to take care of. Now once your technical side of things have been cleared, we come to the external constraints. So first of all being purpose. So for what purpose that particular tunnel is being built. Second will be the finance and contractual obligations, because every project will need some or other kind of financing. So this is something that is taken care of by, let's say, the design contractor or the local authorities, or maybe the work can also take place in tandem with both. Finally, the report to be sent for clearance of the project will be the ground settlements or the overburden settlements, the environmental impact assessment, safety, that is safety during the precondition, that is before tunneling has started, then during the operation, and also the long-term stability of the area. And finally, what technology can be implemented and how it should be implemented. So basically, it's a long chain of process which requires the coordination between multiple departments to get the project into fruition. Now, with that being cleared, so today, since our agenda is 3D tunneling, first of all, I want to show you some examples where 3D tunneling application is required. So first model, if we start from the top left, I'll use the marker to make it easier for all of you, is the presence of a twin tunnel in an hilly region with a fractured zone in there. So this is something that can be done in 3D, because this is a proper 3D problem where you have a varying overburden and a fracture zone or a shear zone relatively close to the tunnel portal. So this part has to be monitored along with the progression of the tunneling part. Second is a ventilation shaft. This is where 3D can be implemented, but again, I will not exactly highly recommend doing these kind of modeling because they are generally very complex, and in any computational model, higher the number of uncertainties, higher the chances of getting it wrong. So the second model from top left, this one, it is completely on the discretion of the user on how they want to proceed with that. Third is the shield TBM. So this part was covered in 2D in the first, in the second presentation that we had, and this is also going to be covered in detail in the upcoming one. Fourth is where you have a varying overburden and you have a pipe roof for support. Now I start with the bottom one. Bottom left is, you can see there is an NATM tunnel and then there are two TBMs working under uh, at a particular depth below it, and there are foundation elements of a existing bridge, and then this is the basement of a building. So this is a proper 3D scenario. So it is again on you if you want to proceed with implementing the foundation pressure, or you can directly model the foundation elements. There are two different ways of doing it. Now this is four poling and roof protection system, and finally a two arch model. Now coming to 3D tunnel modeling approaches in FEM. So we'll have two types of approaches. One is when your tunnel linings are not interacting with each other. That means the assumption is that when the secondary lining is activated, the primary liner is deactivated. Or by secondary, I mean the permanent liner. So this is our first model, and in the second model, both of them are active and operate simultaneously. That is the interaction between the primary and the secondary lining. I'll request all of you, if you have any particular question, please hold them off till the end of the session. I'll be very happy to answer them to the best of our abilities. Okay. So I'll show you a brief glimpse of the numerical model. So the plan of the numerical model kind of looks like this. So as I had mentioned, it will have varying overburden. So this is our tunnel section going here. And the overburden varies from 34 meter, and with the lowest overburden height of 14 meter and highest of 45 meter. This particular area is the damaged zone. So the tunnel goes through here. In terms of supports, we have rock bolts or shotcrete or again final liners, but here we will have some more elements. So this is why this model will be quite interesting for all of you to see. Now, as I had mentioned before, that in NATM terminology, you improvise as you go ahead. So this model also involves certain conditions like that. So where we have certain sections activated and deactivated, or liner widths have been changed at particular areas. So if we take a calculated guess based on our knowledge, I would say, or let's say engineering judgment, if we are approaching the shear zone, let's say from this direction or even from this direction, we have to ensure that before reaching the shear zone, the area near the shear zone needs to be reinforced. By reinforcement, it means some extra reinforcement is needed as compared to, let's say, these areas or this area. So this is what I have done in this particular model, and we will check around. And in the second model, so this is your tunnel, and this is where we only have one set of liner, and that particular liner, when we are progressing with the tunnel, we just apply the change property option to change the property of the liner from your primary shortcut to permanent liner. That is possible in the construction stage methodology. In the second model, you can see there are two liners, the primary and the final liner. So the primary liner is around 250 mm and the final is around 750 mm. With rock bolts, there are around 13 rock bolts for each chainage at a pitch, tangential pitch of around 2 to 2.5 meters. Now for loading and boundary conditions, the loading condition is only self-weight or gravity. We have not applied any extra load in there. Now, in this part, as I have mentioned before, that in the first model, our primary liner gets entirely replaced by the permanent liner. So that is done by using the change property option. So I don't need to create an extra mesh set in there. This can be accomplished directly in here. The construction stage planning, we have a total of 55 stages in here in both the models. So just to have a brief glimpse of the results, the ground deformations. So this is the direction of tunnel progression. Then the shear strains concentration. You can see the shear strains are mostly concentrated on the shear zone part. The geomechanical properties I'll describe you on the model itself. Now coming to a brief glimpse on the results to be expected. The hoops force on the liner, and again this was the shear zone. You can see it is highest in this part, and I have installed steel arches. So steel arches will range from this part till this part. So they are being placed at a distance of 2 meters to 3 meters each, depending on the location or their degree of closeness to the shear zone, or their presence either inside or outside the shear zone. Then the rock bolts. The rock bolts also follow the same trend, that we have reduced the distance between rock bolts when the excavation is quite close to the shear zone and inside the shear zone. Apart from that, then the distance again increases. So you can say this is a systematic bolting pattern, but again that has been improvised depending on the area of interest. Now, you can also say that yes, we have done a numerical model and we can see the results, but again, when I went to the site, or when anyone else went to the site from your team, or let's say my team, they saw some extra areas that had some loose wedges that they wanted to seal off. So yes, you can also apply a rock bolt in there, but again that is a completely field observational method. Then the output, so you can export the output either into the animated 3D PDF format, or you can export the pictures into a Word file, or you can export everything into an Excel file. By everything, I mean the inputs and also the outputs. Or you can just directly export the result snips. So for the short presentation that I wanted to show you, this is what I had in my mind. Now let's come to the more interesting part, that is the numerical modeling. Just allow me a moment. I'll open up the model for you. So this is my first numerical model. So in this particular model, I I have not used two separate liners. Instead, I have used the shortcut liner. Then I have used the change boundary condition. In terms of meshing, we have used the hybrid mesh. Now, most of the design or the support installation philosophies for this particular model have directly been derived on the theory described in the last particular session. So, if any of you who has joined this session only, you can refer to the previous webinar session that we had and get the theory behind it, because both the models are quite big and there are a lot of elements to cover. So we have deliberately omitted that part from this particular session. Now, so my shear zone, my banded sandstone on the extreme left, and this is damage to intact gneiss. So we have three different types of rocks. Now, so what we'll do here is we have used the hybrid elements. So any guesses for why particularly hybrid elements have been used in here? Again, it's a very subjective question. So it's just on your guess that, what do you think? Why would we use hybrid mesh, not a tetra mesh in here? So I have got an answer about faster calculation. Yes, but again, calculation is completely debatable. So any other guesses? It's okay, I'll tell you. The reason for using the hybrid mesh is that if you can see all our quad elements. So quad elements lead to one extra advantages for us. That is the alignment. Alignment is extremely easy and uniform in quad elements. Let's say if you have a quad element like this and you look for the element coordinate systems. So what happens is that with quad elements, they will be aligned in one particular direction. Just activate that. Let's say hide everything. So here the Z is out of plane. That is what we wanted out of here, because it's a 2D element, the plate element. So you can see it is completely aligned. If you have triangular elements, then the alignment becomes very, very tough. That is why in these cases, we always recommend, if you want to check for hoop stresses, directly go for hybrid meshes. This is where you will save a lot of time. Again, calculation time can become less. That is also true. But the primary goal is getting the alignment correctly. So, with that being cleared, if I just show you the tunnel solid, the tunnel has been divided into heading and benching. So if I just show you the dimensions, it's around give or take 10 meters high, and the maximum width is around 12 meters. So given the height of the tunnel, it won't be advisable to excavate this completely at once unless you are not excavating in completely intact amphibolite or granite or gneiss. If you have mixed rock conditions or if you have damaged rock conditions, then yes, it is always better to go for heading and benching. And the true fact being that the rock massif is never intact. You'll always have some reduced strength in there. So that is why we opt for the heading and benching method. So the total length being 140 meters. Now, if I just show you the shear zone, this is my shear zone. So the area in close vicinity of the shear zone has to be reinforced. When I say reinforce, it means it needs extra reinforcement as compared to the or any other area. Let's say this particular area or this particular area. So as the project plan, what I had done was I gave a thicker primary liner on the entry portal and the breakthrough portal, and also during to something like this. Now, if I hide the shear zone, you can see the mesh size here has been shortened up. That means the excavation length has been shortened. So normally the excavation length varies between 2.3 to 3 meters. Is 3 meters in here, but if I come close to the shear zone, it's around 2 meters. Then at the exact center of the shear zone, it drops to 1.5 meters. That is to prevent the shear zone from collapsing. And I had mentioned that we had extra amount of rock bolts in this particular part. So if I just show you the rock bolts near the shear zone, you can see each roof is having one extra pair of rock bolt or extra system of rock bolts. And apart from that, we also have steel arches in this part. So if I just go to property and display the arches, they will look something like this. So my arches, this particular area is completely reinforced with steel arches. Now, depending on your project requirement, you can leave the arches or you can, like take it back. Normally, again, it's a very subjective matter and it depends on your project specifics on what to do with them. In this particular model, I have removed the arches after the excavation has reached, let's say, towards the exit portal. Now, in terms of liners, so we had, as I mentioned, one final liner and the shortcut liner, and also I had mentioned that we had extra reinforcements. So extra reinforcement along with the arches also go for the thicker shortcut in this part. So if I just activate the shortcut mesh in here and I show the properties of the liners, you will see this is your average 250 liner throughout the stronger parts of the ground. In the weaker parts or the parts that are susceptible to collapse, we have a 500 liner in there. Okay, like this. So entry portal, exit portal, and the shear zone. And in the end, we have the final liner. So I hope the inside of the tunnel or the tunnel progression part is clear for all of you. Now, I'll just show you the input material properties. So for liners, I just took out the concrete properties from the database itself. So I think I took M40 concrete grade from the IRC code, and they have been modeled as elastic. For bolt, I just took up properties for steel. So for they satisfy the input material property for both rock bolts and your steel arches. Now coming to the ground material properties. First of all is the shear zone. So shear zone on field is basically a combination of completely fractured rock mixed with some kind of gel material. By gel, I mean it's a filling material. It can be clay or it can be any kind of soil. So the E modulus is around 200 MPa and dry unit weight of 22, cohesion of around 10 kPa, friction angle of 32 degrees. It can also go. It can also be reduced. That is something I had done on the next model. Then the sandstone with a E modulus of around 1 GPa and dry unit weight 27, cohesion value of 175 kPa, friction angle of 42 degrees. Then for intact knees, I have taken 1.3 GPa as E modulus, dry unit weight 27, cohesion 220 kPa, friction angle 45. And also one property of damaged knees that I have taken in the other model. So here the E modulus was reduced by to a factor of around 25%. So the E modulus dropped from 1.3 GPa to around 900 MPa, and the cohesion from 220 to 180 kPa and friction angle of 39 degrees. Now coming to support elements, the bolt have been modeled as embedded beams with steel sections in the section property calculator with 5 or 50 diameter. Then your primary liner is around 350 shear zone liner is around 500 final liner is around 750 and arch is modeled as 1D beam element with a solid rectangle of 100 into 100 So after that, so when we mesh this particular model, the entire model looks like this. Okay, so you can see here the rock bolts have been modeled as the rock bolts have been modeled as embedded beam elements. That is why they do not need direct connections. Instead, they need the mother nodes, that is the ground elements and the tunnel elements for nodal presence and nodal sharing. Now, the ground boundary condition, roller on the sides, fixed on the bottom, allowed to move in one direction only. Then the conversion of the primary liner to the secondary liner. That is done by something called as the change property option, final liner and henceforth. So if we look for the construction stage progression, it will look something like this. For that, I'll just hide the outer mesh sets so that the inner part is visible to all of you. So I'll just play the stage simulation. So in the first stage, all the ground elements are active, no support elements are active here. Then we slowly go forward from there. So I'll just play this thing in a rather slow pace. Just allow me a moment. I'll just try to enlarge this as much as possible so that you have a clear view of the progression of tunneling. So I'll just play the short video. So what you can see here is at any point of time, the maximum unsupported roof area is around 3 meters. We have not gone for more than that. You can do simple hand calculations or a 2D model to check for your how much unsupported roof can be allowed, or when to install the supports using the GRC and SRC calculation. But here what we have taken is bit of a on the conservative side about when to install the supports. And the area on focus should be this particular part. So I have just zoomed into there, so it's clearer for you to see how the excavation planning in shear zone goes ahead. Or I have specifically named two construction stages like this, so that it's clear for all of you to understand. So the 28th excavation is where we start to prepare for enter into the shear zone. That means we are quite close to it. And in the 40th one, we are exiting the vicinity of the shear zone. So just because the shear zone is there, it does not essentially mean that only at the material boundaries you will get the deformations or plastic failure. It can happen even in areas close to it, depending on your ground stress scenario. So if let's say this overburden instead of 45 meters, if it would have been something like let's say something like 700 meters or 500 meters, you could have seen a complete collapse in here with these kind of support conditions, because the stresses would have been that particular high. So that is why, as a preparatory measure, we need to be careful about our approach and exit from the shear zone. And these kind of failures are actually very very common in underground mines, that suddenly the roof has caved in or some particular area of the mine has caved in. So you can understand why. So this is, I think, we are about to come close to the shear zone now. You can take a look here. So if I just hide the shortcut for now and the rock bolts, so my arches are placed like this. If I just go to the mesh set and hide them, you can see how my arches are being placed. Now, so if I run this particular model and then check for the results, it will look something like this. So this particular model had around 54 stages. So the first stage is the in situ stage, where we only need to check for the stresses. Principle A, principle C, or the intermediate, then the sigma 3. So our first excavation. First excavation means first heading. So this is where the stresses get redistributed. That's why you can expect a bit of heaving in there. So if I just go to here and I activate the vectors, you can see heaving in here. So this is what we call as convergence, because your roof is caving in and your ground is heaving like this. So here we have not installed any support. Let's check for the second excavation ground movements. Same thing. 8 mm is the ground settlement, and your heaving is around 9 mm. So which gives a convergence value of 17 mm. That means you have lost 17 mm of space inside the total void. So on the second excavation, we have installed the support on the first heading. So if we look for the forces on the shell element or the liner. Now liners or the area on the boundary will have a bit of high stresses as compared to the area inside because of the boundary effect. So this is your hoop stress. Just hide the rock. You can see it like this. Okay. Then force actual loads on the rock bolts. Second, if you check out the redistribution of the principal stresses, so void, then supported area, then the ground. That is why you can see a high concentration in here. Also, this is where the shotcrete transfers the load to the ground or to the surrounding rock mass. Okay. Then the sigma 3. So if we see the stress result value in here, that can give us a brief indication of how the bending moment or will look like on the shell element. But we will wait for the later stage to check on that. Okay. Then let's directly go to the area just before the shear zone prep. So let's say I go for the excavation 27. Total translations in mm. Okay, so it's in this part right now. So just hide the rock, you can see. Now, naturally, due to the change in the overburden, you can expect the stresses to be extremely high on this part and this part as compared to this part. Next, the forces on the hoof stress on the liners. Let's change it to kilonewton per meter. So right now it is more or less uniform, except on near the boundaries. The bending moment, then the transverse shear force. Now we start with the shear zone prep. So the total translation in mm. So we are exactly somewhere around here right now. So if I activate the coordinate system, this is our x-axis. We'll have to start monitoring the horizontal deformation in the x-axis from now on, because we do not want this shear zone to move, right? So tx translation Let's activate the vectors. You'll see the vectors are pointing in this direction. Then force on the hoop stress on the shell element. And then we look for the shear strains. For now, you can ignore the shear strain on the top because we have a proper cover that will protect the tunnel from any failure in this part. So we are not covering that. But yes, these areas also need to be monitored for any potential landslide or a slow failure. So let's say I go to somewhere between an excavation inside the shear zone. Let's say go to excavation 34, the TZ translation in mm, then the horizontal translation. So if I just also hide the banded sandstone, looks something like this. So here we look at the load on the arches. You can see the compressor load is quite high. And at 40th excavation, we exit the shear zone vicinity. So if I activate the total translation, see this part. So if I go for TJ translation, then the solid stresses, I'll change it to KPA. Now the plastic radius. So we had three different types of rock, both the outer rocks that were the gneiss and sandstone. They had nearly, I won't say nearly, but they had quite close properties in terms of geomechanical ones. But the culprit here was the shear zone. So the plastic radius that we should assume should be from this part. If you go for plastic status, this is how it looks like. You can see, okay. If I just hide the shortcut for now, it will be a bit more clearer. So my damage is quite contained in the shear zone, and this is okay because this is where the the unsupported roof is. So and also this bench has been excavated, so you can expect a bit of plasticity in there. Now finally, the if let's say I go to the breakthrough stage and I activate all the elements here, so our only the benching is left and the final liner will be installed. So if I check the plastic radius, let's go to plastic status. If I go to the right view, you can see. As of now, you can ignore this part, the plasticity in the boundary part, because there will be plasticity in this area. But this is what we have to consider. Then the shear zone. So again, this is an area where I'm not concerned. So is the sandstone area. So I hide the gneiss and sandstone. Okay, I hide the shear zone, the C. So as of now, since the final liner is there, a lot of the damage has already been contained by the presence of the thicker liner. And finally, the last where we install the final liner in here. So I go for the membrane force and hide the rock outside, also the bolts. So this was the slip that I showed you, the shear zone area. Okay, the highest liner force will be in there. So this is where you will need extra reinforcements. Now, here, as I've mentioned, this is the proper non-interaction model. That means right now the liner that you see is the final liner. If I just go to any previous stage or any random stage, let's say I go to the stage number 22, okay, and I apply the shell element forces. Sorry. So these are the temporary liners in this part right now. And this is the final liner when the entire temporary liner or the shortcut liner has been replaced by the final one. So this is one way of modeling a scenario like this. Second way is this particular model, the exact same scenario, but the difference is this, that the temporary liner is present or the shortcut liner is present, the primary shortcut, and then the final concrete liner is also there. Now, if I look for a bit change in the properties, with the shear zone, they are mostly similar. So now here what we have done is, so the question is how to accomplish something like this. Okay. So this is actually quite easy and extremely simple to do in GTS. The trick here is to use the mesh offset thing. So the mesh offset item or tool, if I just show you a new example, it kind of looks like this. Okay, I just take random, random elements. So I'll first of all, let's say reduce the mesh size to 2 meters like this. Let's say I go for a random tunnel section. Okay, I'll just keep everything like that only. And here, let's say I'm not even caring about installing any bolts. Just make a screen snap, post it here. Okay, I'll make the ground, let's say I make a ground rectangle like this. Again, this is for illustration purpose, so do not take the scaling into account here. This is just to show you how to do the offsetting of mesh. Now, so my mesh, and let's say this is my ground. So I'll just intersect everything at first, like this. Then what I do is I'll create a face for the tunnel and then for the ground. Okay, so I'll convert them into 3D. So I'll use the extrude tool, select all. Let's say extrude that not more but 5 meters into the y direction. Okay, so let me auto connect both of them so that I have the connection between both the solids. Now what I do is I just hide the surfaces and the curves. I'm left with only two solids. Now let's say I take any random property into account. I'll just model that as a structural element. I'll press OK, close. Here I'll create one ground element and two or three, whatever it is, as a liner elements. So let's say I put it as ground. Okay. Then I make two shell elements or plate elements. So let's say my initial or the primary support liner is around around 500 thick. Okay. I take it as 0.5. I name it as PSC or primary shortgrid, and my final will be, let's say, 0.75 meter. I name it as FL. So I have two plate elements now and a solid element. So first of all, I'll mesh the entire thing. So let's say I'll start with the 3D mesh definitely. I'll go for the hybrid mesher, select the tunnel section. Let's say my size is 1. I'll mesh this, also mesh this. Now, so I have created and placed the nodes where I needed them to be. So next what I do is I'll just hide the mesh, go to the solid. I'll just keep the inner solid intact like this. Okay. I'll go to extract tool. In the type, I'll select face 1, 2, 3, and its name is PSC. I name it as PSC. Okay. Press apply. Change the property to final liner. Name it as FL. Okay. So my PC and FL, I hide the solid now. So if we look at both these shell elements, you can see they are overlapping. That is true. So if I go to 2D property and activate both of them, you can see both overlapping each other, which is actually not correct. So what to do now? The tool is called offset. So what I do is I'm going to offset the final liner and also the primary liner. So what I'll do is I'll just activate the PSC for now. I'll activate the coordinate systems. They're all pointing in one direction. So I'm on safer side. I'll hide this. So what I do now is I'll go to parameter. I'll click on 2D. In the drop down menu, I'll select add offset. I'll select this. Now the thing to remember is since your Z is on the out of plane direction here, your Z is the actual movement direction. So in direction of plus Z, it is in plus Z, it is positive. In negative Z, it is negative. So what we do now is Sorry for the interruption. So here we all remember our width or thickness of the liner was 500 mm. So we need to offset this by 250 mm. So I placed a distance as 0.25. Okay, press apply. So you can see it has moved here. Then the final liner. The width was 750 mm. So I need to pull it down by minus 0.375. So my final liner is now here and my uh, primary liner is here. So I hope this part is clear for all of you, because to allow interaction between both the elements, this is the easiest and fastest way to do it. And here, since you are modeling them as plate elements, you'll get all your element results like axial loads or the hoop stress, and also the shear forces and bending moments. Otherwise, if you go for solids way, you can also do that. Not a problem at all. But given the choice between two, I'll pick this particular method. So using that particular methodology, I now come to the model now. Okay, this particular model. Same thing. I'll just load up the results for you. So, so everything is exactly the same except we have a new mesh set in here, that is the final liner. The same thing that was replicated in the previous model by the application of change property option. If I go to results now, if I look for the, if I just hide both the elements and activate only the final liner, I'll also hide the rock bolts. Look for the membrane force or the hoop stress. Okay. So the final liner activation takes place from the 11th stage. Like this. Okay. And similar pattern, highest is along the shear zone. So with time, the principle of rock is that the rock starts to heal, as we say, or the stresses start to redistribute. But also with time, the primary support, it starts to deteriorate because of the creep, and the load is slowly transferred to the final support. So I hope the models were clear to both of you in terms of interacting support and non-interacting support. Finally, I had one more thing to show you, that is the portal stability. For that, I had a third model. So here you can see this is basically tunneling into a hill, so which involves the creation of two safety portals, exit, opening, then the lining, concrete lining in there. So at first, and this is the tunneling here is progressing in towards each other. So we start from one this side too and this side too. So in the opening excavation, you can see the behavior of the ground with the shotcrete lining and a factor of safety of 6. That means it is very safe. Also because of the fact that here the rock stiffness taken was extremely high. So that's why you are getting a factor of safety of around 6. Then the exit excavation. Okay. Now, then the movement into the zones. So if I just hide everything, okay, opening lining, exit lining, and it looks like this. So if I just activate the particular outer rock and I check for the deformations as the tunneling progresses, you can see how it looks like. So the final factor of safety is around 4.2, so which is something you can also consider to be very, very safe. So if I just look for the strains, this is how they look like. So in other words, it's just an indication that, let's say someday due to some unfortunate event the slope fails or slope is very close to failure. These are the two directions where you need to place your extensometers or inclinometers or strain gauges or any monitoring equipment. So for today's session, this was all I had to show to all of you. I hope everyone enjoyed today's session.